and this is the final boot camp for Test 1 content. Starting Saturday, I'll be going into Test 2 content and introducing each concepts week by week as a way of prefacing the course, because the whole point of these boot camps is to kind of introduce what you're going to learn in the class so that learning the material when you're trying to learn the material is much easier. And I spent a lot of time, obviously, showing you what it means to do statistics using Excel. And that's our primary focus in these kind of boot camps, as opposed to test review sessions, is I show you what it is to use Excel to do statistics. But since this is the last one for Test 1 content, there is going to be some concepts we're going to go over in addition to just using Excel, so that way you're as prepared as possible for your exam. So I picked 10 really good concepts that will help round out all the boot camps I've done to this point, and help give you a complete picture of, what it is you need to know for the first test on the statistics. If you missed my previous boot camps, this is the third one, so I've already done 2 previously. Feel free to send me a message and I will send you the other 2 videos. So send it to me privately and I'll send you the previous 2 boot camps I've already covered. Okay, with that being said, let's get into this stuff. So the first thing I always bring to everyone's attention is in your lab manual, and you can find your lab manual in Blackboard. And so within Blackboard, if you go on the far left, you see either under course resources or its own tab called lab manual. You'll find a lab manual created by all the instructors at Wake Tech. The math teachers got together and they wrote this lab manual, and they also the same ones who wrote your exams. So the wording is very similar. It's much more similar to how the exam is going to look than your MyLab homework or anything else you do in this course. So to be successful on this test, you have to know the lab manual or you're in trouble. And there are 2 versions out there, and I've snipped 2 important pages depending on which lab manual version you have. So either on page 22 in your lab manual or page 24, you will find something called the Unit Technology Overview. And notice, depending on which version you got, it's the same general formulas. And so they tell you exactly what formulas in Excel they want you to use on this coming test, which means you should not be breaking out a pen and pencil to do these calculations. You should not be using a handheld calculator. You should use Excel for these calculations. And so you'll see for mean and median, we have Excel functions. For range, you can do that calculation. It's also pretty easy to do by hand in that particular case. And then we have our variance and standard deviations calculation. If you need z-scores, we have standardized, and these are the ones that are the same on both sheets, regardless of which version of the lab manual you have. The only exception is on the newer version, the one on the left here is the newer version, we have this added in quartile.inc, and in the past we would always tell people that there's this optional quartile.inc formula that you can use. In either case, it's the same formulas regardless of which manual you'll have. Just depending on which manual you'll have, whether or not it will include that quartile.inc. But otherwise, we have all the formulas on these pages, either 22 or 24, depending on which lab manual version you have. And if you're asking a question, feel free to go ahead. Otherwise, just keep it muted. Okay, so just again, reiterate to you, please have that lab manual. In there are practice questions that are going to be very similar to how you would see them on the test. Now that I said that, let's get into some of these questions where I actually borrowed some questions from the manuals. As always, for those who are new, what I do is I be quiet for about 20 seconds, honestly, probably about 10 because I'm impatient, and then we'll start talking about it. So take a second, read the question, see if you can make sense of it, and kind of in your brain, I would do this, I would do this, I would do this. So go. Okay, first thing we should notice is this is asking for a percentage. And when we see percentage, our brain should immediately think relative frequency. That is our big key word of what we want to do. And relative frequency is just the frequency divided by the total count, how many numbers there are. And so we already know how many numbers there are. It tells us at the very, very top, there are 20 numbers. So we just need the frequency. We need to know the frequency of at least 3,500. And just to remind us, that word at least has a very special mathematical meaning. It means the number we're talking about or more. So when someone says at least, they mean that number or more. In other words, they mean greater or equal to. And so we want to know how many, that's terrible, how many are 3,500 or more? That's the question we're actually being asked to get our frequency, to get the frequency. And so we just need to look at our list and count how many are 3,500 or more. And in this case, my data is sorted, but if it wasn't sorted, I would click the letter up top here, the O. I can go to Home, far right, the A to Z option, and click Sort and put it in order. If it was in order, that's what you would do, but since it's in order, we would just skip that step and start scrolling down and finding 3,500 or more. And we can take a glance down here, and it gives us the count, the frequency. In this case, the frequency is 8. So we now know our frequency is 8. That is a total count of 20, and that gives us the relative frequency, but they don't want just a relative frequency. We need to convert it to a percent. So you click on your number, you go to Home, and you hit the little percent button. Don't be converting by hand. Don't make any silly mistakes. Make Excel do all the heavy lifting for you. Check your decimals just in case there's sneaky decimals in there. Here we can confidently say it's 40%. Next one, we want to find the mean, and we're going to label it with correct notation. So first off, remember we have two different notations depending if we're dealing with population or if we're dealing with a sample. As a population mean, we do this U-looking thing. We call it mu. And then for samples, we use X bar. And we literally call it X bar. And so we just have to decide, are we talking about a population or are we talking about a sample? Well, up here we see a big clue, randomly selected babies. This is a big clue that we're talking about a sample. So we just need to find the sample average, which means we're talking about this calculation right here. And so the method's the same. It still equals average, regardless of which way we're doing it. The one thing that's going to change, and I clicked on the column because all my data is in the column. The only thing that's going to change is what symbol you write with it, what correct notation we use. And so we use a sample average. If it was a population average or a sample average, either way, nothing changes mathematically. It still equals average and then the data. The only thing that's going to change is what label do I put next to it. I'm done with a sample, so I put the average for samples label. But mathematically, the calculation will be the same calculation either way. For standard deviation, recall there's two standard deviation formulas. We have standdev.p and standdev.s, where P is for population, S is for sample. And we already concluded that we're talking about the sample here, so we're going to use that formula. In our symbology for population and sample is slightly different. For our standard deviation for population, we would use this O thing. And then for standard deviation of samples, we just use S. And so, of course, we'd write S for sample standard deviation. And now we can write the formula, equals standdev.s for sample, parentheses, click on the O, close it out, and hit enter. And there's our sample standard deviation. And again, we know it's a sample because we're only selecting some of the babies. These are not all of the babies. If they said that this hospital only had 20 babies and we selected them, then there's no random selection. We selected all of them. But if we're randomly selecting some amount, then we know that there is some kind of sampling going on. And so it has to be a statistic because statistics goes with samples. All right. Now we're going to make a frequency distribution. I saw a bunch of you said that frequency distributions are pretty straightforward. So I'm going to do it a little faster than usual. But at the end, I'm going to show you an alternate formula that you may want to use. You don't have to use it. I don't often show people this formula for histograms because not everybody has this version of Excel. And so you can't always use this formula. So if you try it out and you notice that you don't have the frequency formula that I'm going to show you, you'll have to do it the old-fashioned way. So the first thing we're going to need is the range. If we're doing it manual, which if you know me by now, you know I like doing it the manual way. Then we need to know how many classes so that we can get the exact class width, so that we can then find a rounded class width. And then we can do our LCL, UCL, and our frequency calculation. So our range is the biggest number minus the smallest number. We can look at the data, or we can use the max and min commands, but by looking at the data, we can see the biggest number is 4,000, and the smallest is 1,700. So let's save some time and just type it in, equals 4,000 minus 1,700. Classes, it tells us, it says 5 classes. If it doesn't tell you, you technically get to pick, but by convention, we pick 5, 6, or 7 in the real world. So that's usually your go-to numbers. Possibly just pick 6 that's kind of in the middle to be safe, unless they tell you, in your class, use this amount. But in the real world, 5, 6, or 7 bars when we don't have an indicated amount. So the exact class width, that is the same thing as saying range divided by class. That's our exact class width. So I'm going to click on the 2300 divided by the 5. I got my exact class width. And as you know, we always want to round that up. You can pick 461, you can pick 470, you can pick 480, 500, whatever you like, as long as your first class and your last class has values in it, it's a good pick. And we'll see what that looks like in a little bit. But let's just say I pick 500. That's a nice number above 460 to count by. And of course, this number is flexible. You can pick whatever you like as long as it works out, as long as you have frequencies in the first value and frequencies in the last value. So now we have 5 classes. Just going to number it so we know what we got going on. Our LCL by convention is usually your smallest number, so we'll just type 1,700. And now our class width, to remind us, our class width always goes down, not across. So we're going to look at by adding 500. That value I chose, we're going to add 500 going down every time. So equals the one above it plus 500. And now by doing that, I can go back and grab the corner and drag it down, and it will repeatedly add. If you typed equals 1,700 plus 500, it won't repeatedly add for you. So it's better if you click the cell above it and say plus 500, so that way you can drag it down and it automatically do the calculations. And then again, being fast about it, because we already said we're good at these, we are just going to -1 going backwards. So if that's 2,200, when you -1, you get to 2199. And yeah, technically at 2199 is not 2199, it's 2199.99999999 and so forth, because it's everything before 2200. So now add 500 again and take it all the way down. So now we have our range. And here's the optional part. What we could do is just go through and physically count and write that number down. Not so bad when you only got 20 numbers, but if I had a lot of data going like 400 numbers down, you may not want to do that. And there's actually an Excel command that can quickly calculate for you if you have one of the newer versions of Excel. If you have one of the older versions of Excel, you will not see this function pop up. So notice why I type equal frequency. What this will do is do all that counting for me. The data array is our data, which is an O. So I click on the O up here. And then the bins array is your UCLs. So we're just going to highlight those 5 UCLs. If I close it and hit enter, poof, it does all the counting for me. It went through and found 1 of those, 2 of those, 3 of those, 11, and then 4. This bottom 0 here is your kind of like red flag detector. If this number is anything but 0, so if it's 1, 2, 3, etc., that means that your class width is wrong, and you have to go back and pick a new class width. It didn't work. I'll answer your question at the end, Alexandra, about the testing center and that kind of stuff. But this last row here is just a detector. You want that to be 0. If it's not 0, you need to go back and check your class width. While you read number 2, I will look at Alexandria's question. Let's see. You need to bring anything to the testing center besides our Wake Tech ID? Do we need a computer? So that's a great question, Alexandria. In the past, you had to bring your own laptop, but that was last year. I don't know if it's still the same policy this year. So you definitely should ask your teacher that question before you go to the testing center. In the past, you had to bring writing utensil, ID, and a laptop. But check with your instructor. I don't know the answer and how they set it up for you. When I taught the class, we had students brought their own laptops. Worst case, you can bring it and then just be told you can't use it. Okay. Let's take a look at what we going on. In the description, we can see that we're randomly collecting. So we know again that we're talking about samples. And we have a count of 20 Wake Tech, 20 NC State students. And we're essentially looking at the histogram that shows how much money that was spent on textbooks at a particular semester in time. So the first question simply says to convert this histogram backwards into a table. Usually we take the table and make a histogram. We're going backwards now. And the first part's pretty straightforward. The frequency is just how tall each box is. How tall is each bar? So we have 4 for the first one, then a 6, then a 5, 3, 1, and 1. We're just converting those bars back into the table. The harder part, not really that hard, but it's finding the relative frequencies, which again is your frequency divided by the total. We know the total from here, and we have each individual frequency, so we just need to do that division. And so we would say 4 out of 20, 6 out of 20, 5 out of 20, 3 out of 20, and then 2 ones out of 20. Now, one thing to remember is if it doesn't say percent, you're supposed to leave it as a decimal. So you'd want to leave these decimal answers as your solution and not convert it to a percent unless they ask for a percent. Give it to them the way they want it. Don't do extra. Sometimes they'll mark it wrong because it's a computer grading it and they're looking for the answer written in a certain way. Second thing I want to bring to your attention, which will be a bigger deal in the next unit, is when you're trying to type in these fractions. So notice that all I did was type in that fraction over and over again. I wrote the first number divided by the second number. It's just a fraction, right? If for some reason I forgot and I wrote it without the equal sign, like 5 out of 20, if I hit enter, Excel thinks anything without an equal sign is words. So it thinks right now that 520 is going to be May 20th. It thinks it's a word that I'm trying to write because I didn't put equals there. And so if you start getting those kind of like dates pop up, it's simply because you forgot to put the equal sign out front. The equal tells it I want to do math and not write words. So just keep that in mind because some students get frustrated when they're trying to write these fractions, which you're going to write a lot of fractions in the next unit. Okay. So now we're looking at the next part where it says, based on the histograms, which group of students appear to spend more, NC State or Wake Tech? And so let's use some logic here and try to reason about things. First off, what do we notice about the first distribution? Well, we got a peak on the left and then it dips down. Because the peak's on the left and the tail's on the right, we have a right tail. That's where it's long and flat. We would also call that right skewed. Whenever we have a skew, sorry about that. Whenever we have a skew, though, we know we have to focus on medians. Medians always go with skew. 1 second. I greatly apologize. So medians always focus on skew. The bottom one, though, starts low, it goes up in the middle, and comes back low. So this is the definition of bell-shaped, because the peak is in the middle, and we have tails on both sides. So it's bell-shaped, and since we have, 2 bars away, 2 bars away, we could also say it's approximately symmetric. The bars are about the same length on both sides. And by bars, I mean tails. If this is my peak, I got 2 bars on this side and 2 bars on that side. So we could say it's approximately symmetric too, which means I can call it something like normal, because it's approximately normal because it has both of those features. It's not only bell-shaped, but also approximately symmetric. When it's approximately symmetric and bell-shaped, we can technically use median and mean to talk about this data. But in order to fairly compare the two distributions, in order to fairly compare Wake Tech and NC State, I have to pick the same unit of measurement. I want an apples to apples comparison. If the top one can only use medians, and the bottom one can use median or mean, I pick medians. That's the only one they both can fairly use. So we're going to compare these distributions for typicalness by using medians. And typical just means where is the center? Where is the middle of the data? And so if I have 20 Wake Tech students, and I want the middle, that means I got 10 on the left and 10 on the right, and right there in the middle is my median. Since we have 20 NC State students, it'll be the same idea. So using our frequency distribution, if we were to think about it cumulatively, we have 4. If I go to my next row, I have 6, and that's 10. So my median is right about here, somewhere between the 250 range and the 350 range. It's somewhere in between. We don't know exactly where, but we know it has to be after those 10 and before the other 10. Logically, then, if we do the same thing for NC State, we have 1 plus 3 makes 4. 4 plus 5 makes 9. And so in that range in here, in this 6 box, would be my 10th person. So somewhere after the first one of those 6, right? There's like 6 of them in there. Somewhere after that first one is my other median. And so the middle value, our typical value, is on the first one somewhere around here, somewhere on the left, and then on the other one's way over here. And we know the lower the number, the cheaper the price. And so when we compare these values, which one is more to the left? Which one's cheaper? I hope we all agree it's the first box, the median price of the Wake Tech students. So we would say Wake Tech appears to be typically lower than NCSU because the median price appears significantly lower. Something like that. You don't have to be perfect. It's a time test. They're not going to look for a long explanation, but a couple sentences that talks about either the middle of the data or the fact that one's right skewed and the other one's bell-shaped in the middle. There's lots of ways to talk about it, but that's just how I would focus on it and attack it. Focus on the fact that we can tell that the median price, we don't know what it is, but the median price on the first one is much more to the left than the one on the right. So 50% of the students, the majority of students, are paying less than the other group. Now, that does not mean that every Wake Tech student pays less than every NC State student. Clearly, some poor student paid $500 for a book, roughly. And some NC State student paid $200 for a book. So there are some cases where it is cheaper, but on the whole, on the average, it is much cheaper for Wake Tech students than NC State students, assuming that this data is true and accurate and not biased and created funky by our instructors who wrote this thing, right? Okay. So which measure should we actually use? I actually already answered that, right? Because we're dealing with a skewed right distribution, we would definitely use median. And you would just explain you're going to use median because the data is skewed to the right, because the Wake Tech data is skewed to the right. Because skewed right or right-tailed. Either way. We always use median for skewed data and mean for bell-shaped symmetric data. When do we use mode? You'll see a question later on where we can use mode. But mode would imply that we have discrete units. For mode, we need discrete units, aka classes. And you can see down here that these are not discrete, they're ranges. We don't know what the number is. So we can't talk at all about any kind of mode going on. But in general, for this class, you're always going to pick between mean and median. You can essentially kind of throw out the mode option. We'll use mode to describe things like distributions, but you're never going to pick mode as the primary solution in this class. So focus pretty much, you can almost always guarantee it's going to be mean or median as your solutions, and just decide, is it bell-shaped or is it skewed? And so now what shape is the distribution? I already jumped the gun on that, didn't I? I said that right here. It is bell-shaped and approximately symmetric. So now for the last part, should we use the empirical rule or the 5-number summary? And so what they're getting at here is understanding what does each one actually contain. In order to do the empirical rule, we would need the mean, the standard deviation, and find z-scores. In order to do the 5-number summary, we would need your minimum, your lower quartile or first quartile, your median, upper quartile, and your maximum. And we already said back on C that we should use the median and not the mean. Well, if I can't use the mean, I can't use empirical rule because they go together. These three are necessary in order to do the empirical rule. So the fact that I cannot pick the mean and I'm picking the median means I have to report this as a 5-number summary. And so, of course, we would say we would pick the 5-number summary because the Wake Tech data is skewed to the right, and 5-number summary is best. That's talking about the spread. So the 5-number summary and empirical rules are a way of talking about spread, or how far and spread out things are. And so we would use the 5-number summary to talk about the spread of the data because it's skewed right. Now, if I was talking about NC State, because it's symmetric and approximately normal, I could use the empirical rule because I can use means on those. Okay, quick concept question. Let's see if you can put this in the chat for me. When we're talking about the 36 employees, the 36 workers, is that a population or a sample based on the context of what we see here? What's your idea? Is this a population or a sample? Give me your best thoughts. Yes, great. Yes, these are populations because we're not talking about some. We're talking about all the company they employ. So this is definitely 36 workers, which is the whole entire population. And so what kind of functions would we use for that then? If it's bell-shaped, we would use mean. We would use standdev.p, var.p, because it's population. If it was a sample, then of course those p's turns into s's when you do the calculations. Now, they're not asking for that information, but it's just good things to get in your brain. Are you dealing with a population or a sample? The better question they're asking us is, should we use mean or median? And let's justify it by quickly making a number line. So we think about it, where over here is like no money, and then all the way up to the most paid person, which is a $1 million person. We have the owner, one person, so just one, makes that amount. And then we have $12,000 are made by 5 people. So I'm just going to estimate and call that amount 12,000, and it's going to go up to 5. And then we have 70,000, so close to 12,000, nowhere near $1 million, so maybe over here. That goes all the way up to 30. And then we have that one employee way over here. So notice what we have. We have a distribution that peaks at 70,000, and then it drifts off into this long tail on the right. So we have a right tail, which means that we have a right skew. If it's ever skewed, we always pick median. And so we would pick median because the wages are highly skewed right. And you don't need to worry about the word highly. You'll learn what that means in the next unit. But in this case, it's highly just because these two amounts are very far apart. The 70,000 to the next person down to million, it's a long distance away. Actually, you won't learn about that to test 3. You'll learn how to calculate significance on a hypothesis test. But essentially, you could just say the wages are skewed right and been fine. I just add that word because of my obsessiveness for the language. But more importantly, pick median is the big answer here, because the data or the wages is highly skewed to the right. This one person would distort the findings. And so if I'm an employee, or if I'm a potential employee and I want to get a good estimate of my income, I would not use the mean, because his one salary is going to throw, or her salary is going to throw off the calculation so much that I'm going to walk in thinking I'm going to make 100K or something like that, when in reality I'm going to be much more likely to be making 70K. And how you budget your life based on $30,000 is a pretty significant amount. That's why it's important that you kind of get a good understanding of what is typical or what is the expected value. Now, I know in past boot camps I've done this question before. Forgive me, but it's a very important question because you can sure as heck bet they're going to have sampling methods on this test. So I always like to cover this kind of stuff, even if you've seen it before. So, quick little review. We have convenience. Forgive my spelling. We have cluster, stratified, random sample, or simple random sample. And then we have, brain just went blank, systematic. There are actually more, but these are the only 5 we care about for this class. And we'd like to first parse these by blocking out convenience from the other ones. Convenience is simply not random. People often think convenience means bad, and it doesn't. It's just not randomized. And there are a time and place where you don't want to randomize the data. When we run around and do a census, we actually aren't really doing a census. We only sample because we're not going to get every single person when you do a census. But we're intentionally going to door to door to door and definitely not being random about it. We want to get everybody as much as possible. So you lose that random element, but it's actually a rather important measurement that we're getting. Now, the random part down here, we break these apart. So notice first off that all 4 of these are random. Sometimes students only think simple random sample is the random one. It just has random in the name, but all 4 of these methods are classified as random methods. The ones in the middle, though, they involve some kind of grouping. The first one groups and then does all of a particular group, where stratified does some of each. That's the only difference. They both group them. One does all the group, one does some of the group. Simple random sample, on the other hand, likes to do a large sample with no groups. Just grab a bunch of people and hope for the best. Kind of like your census taking. Just remember, in statistics, a proper census is when you talk to every single person. When I'm using census in the current speak, I'm talking about the federal government running around to everybody's house and trying to get data. So it's 2 different things. But in statistics, when we say census, we mean talk to everybody. When you go and survey an entire population, we call it censusing. So systematic, of course, is every nth number, every 5th person, every 10th person, every 12th person with some kind of system in place. So with that in mind, first one we can notice is that we're making groups. So we automatically know it has to be cluster or stratified. You can rule out the other 3 possibilities. You now just give yourself a 50-50 chance because you can identify that's a group. The next thing we're going to notice is that we got from each level. So that means sum of each. Because it has both of those conditions, we know it has to be stratified. On the next one, once again, divide it to groups. I automatically know cluster or stratified. I can ignore every other possibility. And then reading, all. Boom, big keyword. All, every. Those kind of words. They tell you that it's cluster. So we broke them into groups and then found all of a particular area. So it has to be cluster. Last one. We're looking at the overall group, overall population, so no grouping. We didn't break it, we didn't divide it to groups. And we just got a large sample. Well, that's just a definition of a simple random sample. And right now, you don't need to worry about what's classified as a large sample. You'll learn about that in the next unit. For now, if you just see no grouping and they just talk to a bunch of people, simple random sample. Later on, test 2 material, you'll learn what it means to classify for a large sample as opposed to other types of samples, and whether or not it's sufficiently large. For now, if it's just no group, big selection of people, call it a simple random sample, and don't teeter-totter like, well, is 35 large? I don't know, James. Did they group or did they not group? That's what you should be thinking about. I will zoom in. Now, all this stuff up here is nice and everything, but the real meat of it is going to be down here for A. Let me fix that. There we go. So the first thing I want to draw your attention to is down here, these whole numbers. Obviously, having 2.5 languages, 3.2 languages don't make sense. So down here, we're talking about discrete numbers. Since we're talking about discrete numbers, we now have to consider using mode as a possibility. When it's discrete numbers, we're going to utilize mode to possibly describe the distribution if necessary. And so the first thing you might notice is that we have 2 equivalent peaks. Because there's 2 peaks and they're discrete units, I can call this bi for 2 modal. All that tells the reader is there's 2 values that occur the most. And so that phrasing is one way we can identify the shape of the distribution. It's bimodal, there's 2 modes. If there was more than 2, we would say multimodal for more than 2 modes. And by that way, we're talking about 2 very tall peaks of the same length. But if it's not discrete down here, I can't be calling it bimodal because modes are when you know the exact value. I know that these 13 all had 1, and so it was 1 13 times. If it was something like 1 to 3, I wouldn't know if they're all 1s, if they're all 2s, if they're all 3s. I have no idea. So it has to be discrete and clearly defined values like it is now. So first off, I would describe it as bimodal because there's 2 peaks. And if you box around your peaks, this is what I always encourage students to do so you can figure out your tails. If this is my peak range, then you just have to count how many bars are to the left and to the right to know if there's a tail or not. To the left of my peak range, I have 1 bar. To the right, I have 2 bars. And so technically, it has a very slight or small skew to the right. Because the tail is just a little bit longer. And in fact, if we broke this 5 plus out and had it 5, 6, 7, 8, 9, and broke this 4 out appropriately, you would see a longer skew to the right. And so in this case, my description would be as follows. It is the distribution appears, we like to use conservative language because you may be wrong. So appears to be bimodal with a slight skew to the right. Now, of course, that's the easy part. You just wrote down the same thing you already identified. The harder part is then what does that tell us? What is the point of that? And so when you describe these things in the real world context, the first thing you always talk about is the peaks. And so my peaks are bimodal. The second thing you talk about is any tail. And then the last thing you would talk about is if there's any gap. In this case, there is no gap. There's no place with no data. So I get to skip the gap part. So I only got to describe what does the peak tell us and what does the tail tell us. And so if I were to write about what that means, the second part of the question, what does that tell us? I would first say that it appears that most countries in the sample, because remember, I don't know about the population, but in the sample have 1 or 3 official languages. So see, I'm just adding back to the story, talking about official languages in the story. And then I need to talk about the second part. What does the skew to the right tell us? Well, the skew to the right tells us that some countries have much more than 3, because that's the higher number, right? Much more than my peak range of 3 official languages. So I essentially talked about the bimodal fact. Most countries from the sample have 1 or 3 languages. However, some countries have much more than 3 official languages. And so I'm getting at this tail right here. Notice that we don't talk about the short tail. So I won't talk about the 0 official languages. I don't know why we do that. We actually just don't do it. We talk about peaks, we talk about tails if they exist, and then we talk about any gaps that may happen. So how would it look if there was a gap? Let's say there was no data for 4. Instead, after my first 2 sentences, that would say the same. It appears that we have bimodal, it appears that we have 1 or 3 official languages. It appears that some countries have more than 3 languages. And I'll say, however, there is no country that has 4 languages. If I had a gap, if I had nothing for that area, that's also relevant, telling us that there is no country in the world that has 4 languages. It tells us that whole entire quantity doesn't exist in this country or in any country. So we also like to talk about gaps if they're there. Back to empirical rule versus 5-number summary. And it all depends on how good you justify it. Most of the points are going to be determined by how well you explain your reasoning. Because I said this thing has a small skew to the right, we know if it's skewed to the right or left, we have to use the 5-number summary. Because it is skewed to the right. Not because it's bimodal. Believe it or not, you can have bimodal data and still do bell-shaped information. If I had like 1, 3, then 5, 5, 3, 1, it would go like this. And I have 2 clear peaks at 5 right here in the center. But this is okay for mean because it's bell-shaped. We have a peak in the middle and 2 tails on both sides. So if it was like that, I would actually totally use means to do my calculations. It just so happens that we classified this one earlier as being skewed to the right. And so they're looking for you to make that connection that skewness is 5-number summaries, bell-shaped is means, and you'd be able to make that connection to get your credit. How many? That is just getting at the fact that they want frequency. And we want to have 4 or more official languages. So let's erase some things up here so we can conclude what we're looking for. So looking for our labels, we see the number of official languages is down here, and we want 4 or more. So we're talking about this quantity, 2 plus 4, which is 6. And so that's all they want. How many? They just want the frequency, just the count. The next one, of course, says percentage. That's relative frequency, which is frequency divided by the count. So we want to have at most, and so at most is one of those funny words that tend to throw students off, or phrases. At most means the number we're looking for, or less. So it means less than or equal to. So at most 2 official languages. So 0, 1, or 2. That number or less. And so if we go back to our chart, 0, 1, or 2 is these 3. And so we're looking to add up the values above it. And so we can see that we're looking to add 3, 13, and 7. 3 and 7 is 10, 10 and 13 is 23. So the frequency is 23. We still need our count so we can find our relative frequency so we can then convert it to a percentage. And of course, up here, we can see they sampled 42 countries. And so 42 is the total amount. If you add up 3, 13, 7, 13 to 4, you should also come up with 42. But we're told in the very top, so we're going to take advantage of that fact that we know there's 42. So we're going to find the relative frequency. We're going to do 23 divided by 42. Don't forget your equal sign. And then we'll convert it to a percentage. Home, percent, and then we'll adjust the decimals to whatever kind of precision we need. Right? Don't do any of that rounding by yourself. Have Excel do the rounding for you. And you can do that by just adjusting these little zeros up here. So population of interest is always a fascinating topic for me. Students often see the word interest and they read and find interest and then pick the next thing. Population of interest is not what they're interested in. It's what they actually studied. So we got to be very careful about that they can say they're interested in one thing, but it's not relevant if they don't study that thing. Like maybe I'm interested in high school students' experience in math class, but then I go and study high school seniors in algebra. Well, that means I'm actually only studying, my interest is actually only in high school students of algebra. If you're taking geometry, if you're not in high school, if you're not a senior, I have no interest in you because you're not in my study. So you gotta be very careful that we identify who they actually studied to get the population of interest, because it's that group that we care about. And so when we go here, we can see that they obtained information on full-time students enrolled from the schools mentioned above here. And so our actual population of interest, who we actually studied, are full-time students enrolled in 2-year colleges, 4-year institutions, and private 4-year institutions. So if you're not a full-time student, they're not interested in you in this study. You have the information and gathered in this information has nothing to do with you. If you are at a 2-year private institution, nothing to do with you. So notice it's only if you are a full-time student and you go to one of these institutions, will this study have any bearance on you? So will it actually apply to your defined population? Which is why we got to be very careful. We couldn't just say enrollment from colleges and universities in a state, because there may be students that don't meet this definition of full-time and at one of these institutions. So population of interest is who you actually studied, the group of people, and not just what you're interested in general. So the variable of interest of course, is the information they're getting back that could vary from subject to subject to subject, from person they're experimenting on to person they're experimenting on, or so forth. So in this case, what are they getting back? What's the data they're collecting? Well, they're obtaining the number of full-time students enrolled from school records. So essentially, the variable of interest is enrollment numbers of full-time students at, and you would list out those locations. We're very redundant in statistics. We like to repeat ourselves quite a lot. And so we're looking for enrollment numbers of full-time students at two-year colleges, four-year institutions, and private four-year institutions, because each enrollment amount would be different from college to college to college, or at least could potentially be different. It doesn't have to be different. Every single college might have exactly 60 students. It's unlikely, but it is technically possible. It's the opportunity for variation that makes it the variable of interest. Okay. Next part, categorical versus quantitative. I always remind students what quantitative actually means. It has two conditions, and we often remember the first one, but not the second one. The first one is it must be a number. If it's not a number, we call it categorical by default. Second one is just because it's a number does not guarantee that it's quantitative. So the second condition is it has to be something you can do math. If you can't do math to it, add it, subtract it, multiply and divide, and have that result make sense, then it's not quantitative. So for example, if I tell you my telephone number, adding those numbers up or dividing those numbers doesn't really make a lot of sense. It doesn't mean anything. So my phone number is actually a categorical thing because you can categorize it by my area code or my subject code or different elements of my phone number. If I told you my house number, again, adding those numbers up doesn't really do anything for us. So you can actually categorize it based on whether it's even or odd or a prime number, that kind of stuff, but you don't really do math to it. You can't do any kind of calculation to it. So remember, to be quantitative, it has to have both conditions. It has to be a number first and foremost, but it also has to be something you can do math with. So looking up here, we are obtaining the number, so we know it meets the first condition. And that number is enrollment. So one school is going to say they have 60 students, another school is going to say they have 70 students, another school is going to say they have 200 students. Can we do math of those numbers? And the answer is yes. You can have things like average enrollment. You can look for the modal enrollment. You can simply find how deviated the values are from each college to college to college, how different it is from each location. So we can totally do math of this one. So we would call it quantitative. And when I explain my answer, I would talk about those two features. They're obtaining numbers, check, and it is very reasonable to assume that we can do calculations with those numbers. And that's my brief explanation, just two little sentences. Okay. Now, in order to explain how these four work, I'm going to draw a continuum, a line of sorts, and show you how I like to kind of compartmentalize these terms. On the far left, we'll have simulation, and I'll explain why I'm putting them where I'm putting them in a second. Then next to simulation, we have observation, observational study, if you want to write it all the way out. And then we have survey and experiment. So this is how I like to think about them. And essentially, simulation is no interaction. No interaction with subject. And then over here we have complete interaction. So it's essentially how involved or how much you interact with your subject. And so the more down the line you go, the more you're interacting with them. So a simulation, I type in a bunch of code on my computer and I say, I wonder what will happen if I see how fast the flu could spread in Raleigh. And I hit go, and then this computer would do this analysis for me. I don't actually want to go and give people the flu and see what happens. So it's best to do something like the simulation so I can be safe and hands-off. Observation means that you go there and you physically observe somebody. Like if I want to see how people behave in the lunchroom, I would drive to a lunchroom, sit down in the corner, and write notes as I observe people in the lunchroom. Survey is a little bit more involved because you're actually going to the person and now you're engaging them. I'm pulling out my notepad and asking questions. And that survey experience has an influence on the response. If I go to your classroom, sit down next to you and start asking questions about how much you like your professor, that would be a different experience than if a student sat next to you and asked you how much you like the professor, than if your professor sat down next to you and said, how much do you like them? So that survey interaction does play a part. There's more interaction because I'm actually engaging with you. Then lastly, we have the experiment. Not only am I engaging by observation and survey, but I'm actually doing something to you. I'm giving you a pill, or I'm making you go on a diet, or I'm changing your gas or fertilizer use. I'm doing stuff to you. And so there's a very much involved interaction. So with those hopefully clearly defined, let's go back to the original situation and see if we can figure out, is it a simulation, observation, survey, or experiment? After you read through that, throw in the chat which one you think was done. What did they simulate? Did they observe? Did they survey? Did they experiment? Tell me in your opinion, which one would you pick? In the chat. I see one person say observation. What else? Wait for one more guess, and then I'll move on. Okay. Oh, one more person typing. Let's see what Chris says. So I see a lot of calls for observation. So let's think about this now. So first off, I'm glad we all ruled out a couple of them. I'm glad we all agree that it's not simulation. We're not just typing in buttons and hitting go on a calculator of some sorts. So there's no simulation going on. And we're also not really experimenting. We're not giving any kind of thing to the colleges, no creating a program that involves, there's no actual like implementing something. So we're not experimenting. And so it's one of these two. And so what it really comes down to is did we go and look or did we talk? And you got to think about what's more reasonable in terms of this kind of study. Did we just drive over, go to the campuses and look around and count the students? Or do we call the school up and say, hey, how many students registered? Which one's probably more reasonable? In this case, it's probably more reasonable to assume that we actually surveyed. Now, the big broad definition of observational study includes survey, and often we talk about observational study versus experimentation, but they are technically two separate things. And so in this case, because you're talking to all these different colleges across the state, it would make more sense if we just picked up the phone and called them and asked them to report how many students are enrolled in their school. But yeah, technically you could drive to each institution, go to a good spot on the campus, and then try to physically count how many students they have. That would be observation if you're just looking around and trying to figure that information. So that's the tough part. It kind of depends on how they gather the information. You know, technically, if you're Googling and you're just looking up institution information, that is observation. So it really just depends on whether or not you're going to argue, did they talk to somebody or were they just looking at stuff? You can kind of go back and forth. In my opinion, maybe because I'm older, it'd make more sense to call somebody and just ask them for their numbers. But you can technically argue, which is the whole point, that they're going to ask you to explain your reasoning. And if you can explain your reasoning and defend yourself pretty well, you can kind of fall back between observation or survey. If you think simulation or experiment, I don't care how well you explain it, they're not going to give you credit. So at least we got that part. All right, sampling technique. I already defined these for us before, so let's go back to it. First thing we're going to notice is that they divide it into groups. So we know we have groups. If you know they have groups, you can rule out simple random, you can rule out our convenience, we can rule out systematic. We're down to two choices. Did we go after all of a particular group or some of each? And right here, select it from each type. So some of each. So this is stratified. And if you were to explain your reasoning, they created groups and they got some of each group. Therefore, it's stratified. All right. Well, we got a peak over here, right? We cannot call it a mode because this is a range. We don't know if all 22 are the same value, if there are a bunch of different values. But that's why we use the word called peak, because it is peaking in that range. Can't guarantee it's a mode, but it's definitely a peak. And we notice that it increases on the left and then drops down once you go past that 22. So this long, thin line means it's right skewed or right tailed. And because we're dealing with skewed, we should pick median. That would be our description. And once again, you can pretty much guarantee that we're going to pick mean or median as our two choices. And you just got to decide is it bell-shaped or not bell-shaped. Because it's not bell-shaped, because it's skewed, you'd pick median. This last part here, the last section, I added some more questions because I saw in the pre-survey, a bunch of you noted that empirical rule and z-scores were something that you were concerned about. So I added them on down here so we can actually have a little more discussion because I was going to just stop at this first one. That's why it's really important you do the pre-survey so I know areas to focus in on a little more. The first question is one we've seen in the past if you came to my boot camps, but it's still good practice because you're going to be asked to do things. Now, I already gave it away and said we're doing z-scores or empirical rule here, but what tells us that? If you saw this question, what keyword in A, what big keyword in A is telling us that I need z-scores? Put it in the chat if you know. What's the word here that's popping out to tell you, oh crap, z-scores?
Sandy.
I see in the chat, I didn't quite make out what you said, but in the chat is 100% right. This word relative. This is our key phrase that is telling us that we need z-scores. So they're asking you to make a comparison relative to two things. They're asking you for z-scores. Yes. And so we're trying to compare two different types of things. And when we do that, we compare it by z-scores. So we're going to standardize those measurements relative to their distributions. It's also why Excel calls it standardized, because you're literally standardizing or making an apple-to-apple comparison. And so the first thing we're going to just do is make some notes on here. We're going to need Malik's information and Sylvia's. And for Malik, we're going to need their observation, their actual measurement. Then we can have our average measurement and our standard deviation so that we can have our z-scores. Malik's actual measurement was 50. Sylvia's measurement was 51. Malik's measurement average for his group is 71, and the standard deviation is 11. For Sylvia, it was 80 and 14. So we will be able to compare them into an apples to apples comparison because Malik has a smaller number than Sylvia, but in general, men have smaller numbers than women. So it's not really fair to compare the two. You know, compare me and my wife's a lot smaller than me, and so I can just generally lift more weight than she can. But the real question is, can I lift more than other men as much as she can lift more than other women? That's the real fair comparison there. That's what we're doing. We're doing these z-scores. So for our first value, we're going to say standardize, and it's literally telling you the x value, the measurement, the average value, and then the deviation. Click the 50, comma, click the 71, comma, click the 11. Close it, hit enter, there's your z-score. You could also, if you prefer to do that fraction thing, just remember your parentheses, and it's observation minus average, close your parentheses, divide it by your deviation. That's the official by hand calculation, but it's unnecessary. You have an Excel function, so take advantage of it. It does the same calculation either way. So again, standardize, observation, the actual measurement you can see, the average, and the deviation. And so now we're being asked, which one is the lowest one? Which one is the most negative in this case? And I hope we agree that the more negative it is, the smaller it is. And so in this case, Sylvia is the lowest one, or lower one. When they ask for your answer mathematically, you show them this. Show them your calculations. Now, when we're talking about usual or unusual, unusual is defined as either being greater than 2 or lesser than -2. In other words, more extreme than plus or minus 2. So 2.5, 2.6, 2.9, 3, 4, 7, all those numbers are more extreme. -2.5, -2.7, -2.9, those are all more extreme. And in this case, again, Sylvia's happens to also be extreme. It has to be past -2. So we classify her as unusual. And so is anything unusual? Yes. Sylvia is unusually low. Unusually low. So notice that even though Malik's score is negative, that means it's low because it's below 0, but it's not unusually low. It's just low. And so even though he's lower than average, he's actually classified as normal. It's normal to find people between -2 and 2 Z's. That's what we call the normal or usual range. So it's expected to find somebody between -2 and +2 Z's. It's not expected to find somebody beyond 2 or -2 Z. And so Sylvia is definitely just unique and something different about that person, while Malik is pretty much on par. It's expected to be within those ranges. More practice. And again, looking at A, you can quickly see our word right there. That relative word is telling you once again, I need Z-scores. So we have the Hereford, I don't know if I'm pronouncing that right, and the Holstein. We need their measurements, we need the average, we need the deviation so that we can have Z-scores. The Hereford.
Can I ask a quick question?
Sure.
Sorry to interrupt, but
No,
like,
go
remember, I was in like your second boot camp, and you remember when you said like, I think if it's like 3, 2, 1, 0, -1, -2, -3, was that with Z-scores? Like, can you find
Yes.
Z-scores that way too?
You can when it's talking about the empirical rule, which we're going to do for number 10.
Oh, empirical. Okay, got it. Okay, sorry about that.
No, that's a great question. I don't mind being interrupted, so please, that's fine.
Okay.
All right, so the Excel calculation method, the one that we just did, notice that these values are continual, they're decimal values. You cannot use that 3, 2, 1, 0 method to calculate decimals. And so when we're doing relative comparisons, you definitely want to use the standardized function. When you get to the empirical questions, like when it says use the empirical rule, that's when you get to do the 1, 2, 3, 4, etc. And you'll see me do that in a second. It's a nice alternative when we're dealing with whole numbers. And the empirical rule assumes you have whole number calculations, while relative comparisons do not, in which case we have to use the standardized function. So the Hereford weighs 96.6. Oops, wrong spot. 96.6. The Holstein weighs 99.5. The average Hereford is 78.7. And the average Holstein weighs 89. We got standard deviations of 8.1 and a standard deviation of 7.5. So now we just need these calculations. And by the way, the reason why I said you can't do it by the 3-2-1 method, just so you can see it, the 3-2-1 idea is when you start adding your deviation to your average repeatedly to try to get the observation. And if you do 78.7 plus 8.1, that's equal to a z-score of 1. That's not 96.6, so we would add it again, plus 8.1, 94.9, and plus 8.1. And so just to be clear, this is equal to a z-score of 1, a z-score of 2, a z-score of 3. But I want 96.6. None of those numbers are 96.6. We do see that it's between 2 and 3. So when I do this calculation, I'm going to get an answer between 2 and 3, but I won't know the exact answer until I use that Excel function or until I do the formula by hand, the parentheses way. So equals standardize, 96.6, 78.7, 8.1, close it, hit enter, and look at that. It is in fact between 2 and 3. It's right between those values. But that's the precise location, this continual value. Z-scores are continuous calculations. They're not always whole numbers. And so that when you need a value that's not from the empirical rule, not these counting down by deviations, you can't do it by just making a table. So unless you see empirical rule, you're going to have to use one of these kind of functions. So for the other one, standardize, our observation, our average, our deviation, and there is our z-score. And the question in this case says, which one is heavier? So which one is more? And I hope we agree that 2.2 is bigger than 1.4, so the first one is more. So in this case, we would say the Hereford is heavier. And the mathematical explanation would be the calculations you did to the right. And of course, both of them are positive, so they're both above average. What we want to know is any of them considered unusual. So this significantly high is the same thing as saying unusually high. And again, more extreme than 2 is how we define it. They technically both could be more than 2 or both less than 2. So it's two different questions. The relative question just wants to know which one's bigger. The other question is, well, is it significantly bigger? Is it, mathematically proven to be bigger by being bigger than 2? And yes, the Hereford is above 2. So you would say, yes, the Hereford is significantly, so sig, high, because the z-score is above 2. And that's it. If they both are above 2, then you would say both of them. If neither is above 2, you would say no, none of them are significantly high. You can be better than your friend, but not good, essentially. Now, as that was just asked, we're talking about the empirical rule now. With the empirical rule, we're going to make z's a little differently. Instead of worrying about calculating these precise decimal calculations, that's what we're doing up here. We're calculating very precise z-scores. We're going to make a generalized chart and then utilize the chart to use some facts. One fact is if you have a z-score range from -1 to 1, the percentage that we associate with that is 68%. If you have a z-score from -2 to 2, we associate that with being 95%. And if you have a z-score from -3 to 3, we associate that with 99.7%. These are rounded values, but these are the ones that we just by default associate with them. And what we're going to do is have measurements on one side, z-scores on the other, and we're going to only focus on whole number z-scores. That's why you don't need the calculations. We're just going to worry about the actual whole numbers. And so our average score, our average actual score, is equivalent to saying a z-score of 0. They're the same thing. And then every time I increase my average by adding the standard deviation, I increase my score by adding 1. And so let's see what that looks like. In this case, our average was given to us as 176. 176. And I need to go 3 deviations bigger, 1 deviation, 2 deviation, 3 deviations. So we're going to add this deviation 3 different times. The first time when I add 7 to that, 176 plus 7, that's 183. If I add the deviation again, that's 190. I'm just adding this 7 every time. If I add 190 and 7, I get 197. So the first time I added 1 standard deviation, I added a second standard deviation, I added a third standard deviation. So z-scores are just how many standard deviations did you add or subtract. When it's a whole number addition of deviations, it's nice, z1, 2, 3, 4. Sometimes, like I showed you earlier, you'll deal with decimals. Fortunately, our empirical rule calculations are always done with whole numbers. You'll learn in test 2 what you do when it's not. And now to go down, we're going to minus standard deviations every time. So 176 minus the standard deviation, which was, forgot, 7. So we're going to do 176 minus 7. And so that's 169. And then if I minus 7 again, that's 162. And if I minus 7 again, that's 155. And so I went down 1 deviation, so minus 1. I went down a deviation, minus 2. I went down a deviation, minus 3. And so whenever we're dealing with the empirical rule, it's to your benefit to make a chart kind of like this. Because now to answer the question, we just read off the chart and we get our solution pretty fast. So looking at the chart, they're saying we want the percentage from 169 to 183. Here's 183. Here's 169. What z-scores are we talking about? We're talking about the z-scores of +1 and -1. And when it's +1 and -1, we're talking about 68%. And that's it. You just read off the chart. The next one says 155 to 197. Let's change color. 155 is down here. 197 is up there. So we're doing -3 to 3. And again, right off our little solution key, we know the answer. Not so bad. Once in a blue moon, you will get asked about values that are not the same number on both sides. Like if it's 1, 1, we know the answer. If it's -2, 2, we know the answer. If it's -3, 3, we know the answer. But what would happen if they asked you for something like 190 and let's say 169? Well, 190, that is a z-score of 2. Let's write that down. And the 169 is a z-score of -1. And so if you notice, there is no values on here where it's just minus 1, 2. It's either -1, 1, 2, 2, 3, 3. And so what do we do when it's 2 different numbers? Well, that's when you have to do a little bit of math. So we're going to draw a little bell-shaped graph. Nothing fancy, but we know empirical rule requires bell shapes. And we're talking about the 2 range and the -1 range. So we know with 2, that's always paired with -2, because one of our facts over here. And we have -1 and +1. And by the way, in the middle here is 0, so 0 to 1 to 2, 0 to 1 to 2. That's why I knew to put the 1s on the inside and 2s on the outside. And we're going to use our facts on the left here to figure out what it is from from +2 all the way down to -1. So we want to know how much is this space. That's what we need to figure out. And we already know this inner piece. From -1 to 1, we know, according to our information over here, is 68%. What we don't know is how much is it from +1 to 2. If we knew that, we would just write that down and get the answer that we're looking for. But we don't know from 1 to 2, so we got to do a little bit of math. We do know if I go from -2 all the way to 2, that's 95%. And so if I subtract these two, then what that will tell me is how much must be on the sides, the difference, right? And we know bell shapes are symmetric, which means however much is over here, it's the same amount over there. So if I subtract those two numbers, I can then just cut it in half to find out how much goes in each of those parts. So let's do that. We have 95%, take away 68%. That's 27%. So that means that this 27% must be broken up to go into these two spaces. So just divide it by 2. And so that comes out to 14%. And of course, if you weren't sure, you can go up here to home. And actually, it's not 14, is it, James? It's 13.5%. Always check your decimals. So that means that the one side on the left is 13.5%. And the one on the right is 13.5%. And if I added 13.5, 68, and 13.5, I'd get that 95, that from 2 to 2 range. Of course, we don't want 2 to 2, right? We only care about from -1 up to 2. We only care about those two measurements. So we just need to add them up. We need to take the 68 and add the 13.5. When you add them up, you get how much of a percentage we're looking for. And so 68% plus 13.5%. It's 81.5%. That would be the solution they're looking for. In general, especially for the first test, it's going to be one of the -1, 1, -2, 2, -3, 3. Just once in the blue moon, you'll get this extra part where they throw out there where it's not the same number. And so I always remind students how you can find it when it's not the same number. Just a heads up. But most of the time, you're going to find that it's going to be one of the basic 3 empirical rule ones on the first test. And you'll learn for the next test what we do when we're dealing to find the empirical probabilities when it's not whole numbers. Like if I want to find this calculation up here between these two z-scores, you'll learn how to do that in the next test, next unit. And if you come to my boot camps, you'll learn it from me in the boot camps as well. All right, my friends, that is the last of the boot camps for Test 1 content. If you're interested, this Saturday or next Tuesday, I am hosting Test 2 content material. I'm going to start introducing it. And as always, I introduce content before you see it in class so that when you go to class, it's a little easier to digest and you can focus more on learning the material and less on learning Excel. As always, I hope this information was helpful. I will place in the chat a post survey where you can give me some feedback, and I will look forward to seeing you either Saturday or next Tuesday.